So here we have it's a new topic for discussion, and it's about how we can perform voltage control uh, in the system. And since voltage control is related to reactive power compensation, so because the previous topic, in fact, the earlier topics what we had, it was on active power control and frequency. So the same way, because the frequency variable in the system depends upon the active power balance between the generation and the load demand. Same way, the voltage control, the voltage quantity in the system depends upon, you can say, reactive power balance between the sources which are responsible for the reactive power generation and the loads which consume reactive power, or there are some other components which consume reactive power. So says in the system, again, in a similar way, we need to have a balance for reactive power and thereby achieve the voltage control. Uh, but there is a little bit different because when you talk in the perspective of active power and frequency control, because there the sources for active power, it is only your generator coupled with the turbine. So you have the active power generation from the turbine and the synchronous generator. And your consumption, that is from your load demand side. So in respect to the active power balance, it is between the generator and your load only. But nothing in between the source and the load, generator and the load, right? But when you talk about in the terms of voltage control or the reactive power balance, then you have not only the sources, in fact, sources from the generation side, that is the generator, but there are some other components. Even which will be, which can be, in fact, which can be a source for reactive power, or uh, it can also consume reactive power. So the reactive power generation, in fact, and the consumption in the system will depend upon what is the situation. And thus the voltage control is little bit much more tricky as compared to the active power and frequency control, because there are several components involved towards the reactive power, either source or a lower consumption. So, so with this topic in discussion, the some of the goals that you will have at the end, you will know what are the methods which can be for reactive power compensation or the voltage control. And but here we will talk about the compensation on the generation side, or the voltage control on the generation side and the load side here. Then we can we will also discuss what are some of the equipments here for the compensation on the voltage control application. I mean, there will be some discussion on the characteristics of these reactive power compensators, which we use for the improvement in the voltage profile. And also what are the techniques, voltage control approach in the power network. Now, here our part of the discussion will be limited to transmission network, right? That means we will have the discussion about the reactive power compensation or the voltage control at transmission network. But just to give you a little bit, uh, nowadays even the distribution network, right? So where you have the renewable integration. So when you have the renewable integration, let's say from the PV system or from the wind system, and mainly at the distribution network. So now when you have a distribution network integrated with the renewable resources, so we have the regulations now from the system operation side that these renewable generation resources, they should they should in some way be able to have some amount of compensation and thereby contribute to voltage control in the network. So it means that uh, uh, now we have the policy that it is not only the synchronous generator based resources, they should have the responsibility, or the uh, reactive power compensators which are installed in the transmission network, they are responsible for the maintaining the voltage in the complete grid network. It is said now that since we have a high amount of renewable integration in the system, and mainly at distribution network, thus the policy framework has came into existence, and it is said that uh, some way like smart inverters which we use in the PV system. So these smart inverters in some way they should contribute towards the reactive power compensation or the voltage improvement at distribution network. So thus it is very important that not only you have the reactive power compensation and the voltage, and you talk about the voltage control not only at transmission network, but also now we say at even at distribution network. And this there is a policy that it has to be achieved through the renewable components, renewable generation components, to let's say the smart inverters, or even we say that wind farms or the wind systems, they should also some way contribute towards the reactive power compensation, and thereby the voltage profile improvement in the transmission network or the distribution network. Yeah. So, but here in our part of the discussion, we will only focus on reactive power compensation or the voltage control at transmission network only here, right? Anything on this discussion? So we will not be discussing about the voltage control through a smart inverter, or that you get it from PV system. So we will not discuss that part here. Okay. Or maybe the voltage control achievable through the operation of wind systems. So we will not discuss that part. Now, what are the objectives here towards the compensation that we had at in the system? Uh, First one is refers to the equipment security, and we because it is very important that the all the equipments that we use, uh, either at the utility end or the consumer end in the system, they are subjected to a standard voltage at their terminal. So it means that if I say the voltage rating of your appliance, less the domestic appliance, single phase, you have 230-volt AC. So thus, at the consumer and at the terminal, the switch point, you should get 230-volt here. So thus, it should not be an over voltage at the terminal where you connect your appliances. That's a single phase appliance. So it should not be an over voltage, right? So it will say that the voltage which is available at the consumer end where you connect your appliances, that should be within the limits, and so as to avoid any damage of your appliances. Yeah, and thus we want our equipment to be secured. Second part is that because we want the system uh, integration, and we talk about the voltage stability in the system, and thus here we talk about that the the voltages at every buses in the interconnected system, that should be within the limits. And here we talk about voltage stability in the system, and in fact it will be the voltage and the reactive power control. They will have significant impact in ensuring the system stability here. So that, as I said, uh, if you are able to achieve reactive power in the system, then you can maintain voltage at every buses uh, around the nominal value or the acceptable range, and thereby ensure the system stability. If you remember, in the beginning of lecture, we had different we have discussed the classification of power system stability, and based on variable to which the stability is associated. In that case, we have the rotor angle stability, we have the frequency stability, and the third one is the voltage stability. So thus to maintaining the system stability, voltage control or the reactive power compensation or the control that is important here. And then the third point that is again it is also an important, and as a towards the objectives of reactive power compensation is having or achieving higher efficiency of power transmission. So the reactive power flow remains minimum, because because we want to reduce these losses that will take place when you have the power flow through your transmission network. So thus if you are able to reduce these losses, then we can have more amount of real power flow uh, in the network, and thereby have higher transmission efficiency here. Can you guess what is this I here? How this reactive power flow can be maintained minimum? What is this I then?
Isn't this the current flowing through the lines?
Yes, it is current flow through the line, but if I say, what is that? I'm not able to write here. Okay, just wait. If I do it here. Uh, okay. Why it is? The load current flow will be a sum. It will be a phasor sum of active current flow and reactive current flow, because you have a AC current flow, right?
Mm-hmm.
Okay, right. So just wait, I'm facing some problem here. Why it is no? Why I'm not able to use it? Okay, yeah. So this is load current, right? Now this load current flow will be active current flow plus J of reactive current flow. So this, because this is the net current flow, the resultant current flow in your line. Yeah. That will have some component of active current and some component of reactive current. And this will depend upon what? Which factor, which component can be more or which component can be low. It will depend upon what?
The power factor of the load,
Power
huh?
factor. So, yeah. So if you have better power factor of your transmission line, so this component will be higher, right? And thus thereby this component will be lower, and thus the losses through the inductive element of the line and the losses to the resistive component, yeah, resistive element of the line, because of this current, inductive current, or I must say, because the I say power factor is lagging, so because of the reactive current can be it can be maintained minimum, and thus you can have more amount of real power flow through the line. Yeah, that means this one, and thus you can have higher efficiency of your transmission network here, right? So that is one way, and thus it is important that we are able to have the in fact, we will discuss later on that your transmission network that can be a source or a sink for reactive power. Source means when I say it is can be it can generate reactive power, and when I say sink means it will absorb reactive power, and thus your transmission network can be as a source or a sink for reactive power. Yeah, right. So next one is what is voltage instability or what is voltage collapse here. Though we had earlier also discussed voltage instability, uh, what it basically refers that the voltages at the buses in your interconnected system uh, goes down. That means it falls below beyond the acceptable limits. Yeah. So, for example, if you have some bus network here, you have some bus network, and let's say that V1, we have V2, we have V3, we have V4, and you have the load also here. You have the load, right? And let's say you have some generator connected here, fine. And here also you have the load. Now, if the voltages at these buses uh, reduces beyond the limits, acceptable limits, then the voltage instability will arise. And although here it is said uh, if it is beyond zero 0.8 per unit, but uh, normally we have in the range of 0.9 or 0.95 per unit here. So that could result into the voltage instability. And then again, one more point that if the voltage drop at this bus network takes place, that means, let's say you have, I will discuss later on. Let's say this is a load here, right? And you find that the load at this bus, this is the load, that means the power drawn by the load. You are increasing the power drawn by the loads keeps on increasing here. And here the voltage should be 1 per unit. But let's say for a low amount of load, you have a voltage maintained. But for a certain range of amount increase in the load, the voltage drops here. And let's say the voltage drops to something 0.9 here, 0.9. And if you further overload here, if you further overload, then the voltage will collapse, right? So that means beyond a certain point of overloading, that means the power drawn by this load, the voltage collapse takes place. So when the voltage collapse takes place here, then what would happen? Hmm? Can you say?
I mean, if the voltage reaches zero, then the load will not receive any power, right?
Yeah, lot to not receive power. So because remember one thing, the system is synchronized. Your bus network is synchronized, and it is said that one of the conditions for synchronization is that the voltage should be the same. The voltage magnitude of the interconnected system should be same. So if this bus has a voltage collapse and beyond the limits, that means this bus will be desynchronized from the remaining system. All right. And as a result, because of the voltage collapse, uh, rotor angle instability will get take place. It will get initiated. So in fact, here voltage collapse takes place, and that is the voltage instability. And later stage, it is the rotor angle instability which is transformed, right? So in the system stability, when you look at, uh, it is the voltage instability, and at a later stage, because at this bus, the voltage collapse takes place, and then later stage, it will be translated. The system instability will get transformed into rotor angle instability here, right? So earlier also, if you remember, maybe in the beginning, I said that whatever the blackout which we have come across in the system, eh, the it was not just one form of instability that was responsible for the blackout occurrence. Initiation of instability due to one and transformation into another instability takes place, right? Do you remember I referred this statement? So here voltage
Yeah.
collapse takes place, and so voltage instability at this bus, and then later the system instability is transformed into rotor angle instability here. So this is likely to take place, and thus the main factor uh, which is uh, which causes the voltage instability is the inability. Why voltage instability can arise? This can take place if you are not able to in your power network maintain a balance uh, between the reactive power, and thereby if you are not able to control the voltage at the bus. So it is important that you maintain a reactive power balance in your complete grid network here, and thereby achieve the voltage regulation at every buses. So, so the question arises about the reactive power balance here. Earlier, we talked about active power balance, and thus we set frequency control or frequency regulation in the system. The same way here we talk about reactive power balance and thereby voltage control at every buses in the network here, right? Right. So next one. So we continue. So the driving force for voltage instability, mainly what we have experienced. If you refer here, I said we about this voltage drop and the voltage collapse. I had this example where you have the increase in the load demand here. So the main factor that had been responsible towards the voltage instability, uh, it is mainly the load here, load connected to your bus. And uh, some cases you may also have voltage instability due to the loss of the load. Let's say sudden, in fact, it is not only the loss, but it can be also increase in the load. Both it can be. And then once you have this situation, then the system integrity loss. So that means the because you have the system operation in a synchronized way, and if one of the bus, yeah, if one of the bus experiences a voltage collapse, then this bus will get desynchronized from the remaining system, and as a result there will be unbalance in the remaining system as well, and it is possible that you come across even cascaded outage. Yeah, it is possible. So there we that's why we say the system integrity being lost here in your complete network. To give you about what is the time frame uh, uh, which we normally have for voltage stability or voltage instability. Uh, do you remember for what is the time duration which we come across for rotor angle stability, instability, and how many seconds voltage instability can take place? Do you remember?
I don't know, maybe 1, 2 minutes. I don't know.
1 or 2?
Minutes?
No, no, this is too long, longer
Really?
time duration.
Okay, a few
Uh,
seconds then.
yeah, if I consider the first swing in stability, because maybe I have draw it here something, because let's say you have this is your delta here, and this is your time in seconds, right? This is in second, and let's say that you come across rotor angle oscillation here. All that following some disturbance, you come across rotor angle oscillation. But depending upon what type of disturbance it takes place, it is possible that uh, you can have the first swing instability, and I can say, like, let's say the rotor angle increases and then it goes beyond. This is an example of first swing instability, and that could be something 1 second or 2 second here, something. So that means in 2 seconds you lost your system stability due to the rotor angle here, because here you find the rotor angle goes out of the step with respect to other machines here. It could be possible that the rotor angle follows one swing, but thereafter it going beyond. So this could be an example of second swing instability. It is possible. So here it could be saying that it is something 3 second or 3.5 or 4 seconds something. So after the first swing or the second swing, rotor goes. That means the it is the out of step with respect to other angles in the buses. Yeah. So thus the rotor angle instability is much faster. What I mean to say here, right? Just see, if I say 1 hertz of oscillation, 1 hertz, what does this mean? 1
One
hertz of,
hertz?
yeah. So one cycle in 1 second.
Yeah, 1 cycle in 1 second.
one
Yeah.
second. So this is, so if that means one cycle of oscillation takes place in 1 second. Yeah. So this is one's Hertz oscillation, right? So I am talking about the low frequency oscillation, right? So if you have one cycle of oscillation in 1 second, this is 1 Hertz oscillation. And thus that means if I say after one cycle, the instability takes place, let's say due to some disturbance, severe disturbance, right? So after one cycle, that means after 1 second, instability will arise. So thus here, when you talk about the rotor angle instability, it is of much shorter time frame, much shorter time frame. 1 second, 2 seconds, 3 seconds, or maximum 4 to 5 seconds, instability may arise. But when you talk about the voltage instability, here again we categorize into two different time duration. One is the short term, or we talk about the transient voltage instability. And in this case, this could be in the range of 1 second up to 30 seconds, something. Yeah. So this is much faster. That means voltage drops takes place at a faster rate. So that means, and this could take place if you have a large amount of dynamic load being connected suddenly at a bus. If you have a large motor connected to the bus, all right, and then the motor will draw, because the motor is inductive in nature, right? And the motor will draw a high amount of inductive current from the bus, and as a result, the and if you are not able to uh, compensate this much amount of inductive current which is drawn by the motor at that period, during that period, then the voltage at the bus will drop. And this can result into voltage instability in a shorter time frame. Then another one is that could be control action through the AVR on the excitation system of the generator. So if you apply some kind of limiter on the over excitation of the generator, because you don't want to have heating in the field winding of the generator. So if this control action, or you are applying some limit in the operation of the AVR to the excitation system, even in that case, voltage instability may arise here. But this is at the generator bus mainly, but this could be at the load buses basically. And in some cases, we have the time duration of voltage instability, let's say from several few minutes up to several minutes. Let's say that at the load bus, right? At the load bus, you have tap changers or the voltage regulators, and then you have a gradual increase in the load. You have a gradual increase. It's not a sudden increase in the load at the load bus. It is a gradual increase in the load at the load buses. And though you are able to have the operation of tap changers or the voltage regulators, but they are not sufficient. But if they are not sufficient to sufficient enough or effective enough to provide the voltage regulation, that means the voltage improvement uh, through the tap changing in their windings, then they may have voltage instability, resulting into voltage instability. And but this could be of much longer duration. Similarly, even in the case of generator bus through overexcitation limiters, uh, if you have slow gradual if we apply the limiters in a gradual way, so this could take place in a longer duration here, right? So just to illustrate you, this is the PV curve here. And you can see that this on the x-axis, it is the active power loading. So that means if you have a large amount of power flow, or you have high amount of power drawn from a given bus, right? So that is the active power here. The loading on the line, you can say, or the loading on the given bus, you can say. And if you have low amount of power flow or the loading in the bus, then the voltage can be maintained here. But if you go on increasing the load, then the voltage has a drop here. And this could be, let's say, from this could be 1 per unit here. So as you load the line, or the load, or you increase the load on the bus, voltage will drop. So it could be like something 0.98, 0.999, 0.98, 0.9795, and so on. So up to this point. So this could be the safe operating region. But let's say you have something 30% overloading, right? So if you have a 30% overloading, then okay, you can have overloading up to this margin, right? So, but if you further overload beyond this point, so let's say it is something beyond 40% overloading, then you find that the voltage drops much more faster rate. So the drop in the voltage, uh, it is much more. The slope of the line, when you refer, it is much more here, and thus is, you can say, the margin here. And but if you load beyond this point, that we call it as nose point or the knee point here of the PV core. And this beyond this loading beyond this point will result into, it will result into a voltage drop, and that is the unstable operating region here for the system. So in fact, this point, you don't get it actually. You don't get it. If you load it beyond this one, suddenly the voltage will go down. You don't get a different point here on the curve. It will be a sudden. So basically what you find that it is basically voltage becoming zero at the bus. What does this mean? If the voltage becomes zero, what does this mean, signify?
It means the voltage has collapsed. But
Yeah,
I have a question here. Why is it when the voltage is zero, you still have some power transfer?
it will still have.
I mean, here the curve, I thought it should reach zero, like it should reach the origin, but it stops here at some value
Uh,
of power.
yeah, right.
Why is that the case?
Okay. You mean to say why does not the curve reach here, right?
Yes,
Yeah,
yes.
but one more thing. It means that voltage becoming zero, but the load remains connected. That means there will be a current flow to the load, right? There will be a current flow to the load, and voltage becomes zero. It means like it is like a short circuit here, right?
Okay.
So the situation is similar to a short circuit, because in a short circuit, voltage becomes zero, but you still have some current flow to your load.
Mhm.
So that is the situation we come across here. Voltage will become zero, and then you have some current flow. And this is the situation it referred to the short circuit situation here, basically. Because you cannot, because if you increase the load beyond this point, and let's say if you at that instant you suddenly cut out your load completely, you, the moment the voltage collapse takes place, at the same instant, if you cut out your load, if you tip the load completely, in that case this will become zero. right? But this is not does not happen actually. You still, because you are increasing the load, you are increasing the load step by step. You are increasing the load is step by step here, and then you have a drop in the voltage. Yeah, you have a drop in the voltage. And but if you increase the load, let's say at this instant of time, then the voltage suddenly goes back. This is what happens here, in fact, right? Okay, so that's to discuss more about this we have. So I have this curve. I got it from internet actually, and you can see that this is the initial voltage here, the bus voltage. This is, you can say, the rated value of 1 per unit here. And here they take an example because this is the duration which is said as in some seconds here, right? And thereafter a few minutes here. So normally the moment some transient disturbance takes place, let's say the most severe on the fault. So if it is a temporary fault, right? So I say a temporary fault of something of 80 millisecond or 100 millisecond something. So if you have a temporary fault, then the break, the relay and the breaker will operate, and then the line will get disconnected, and thereafter again, since it is a temporary fault, the breaker will try to reclose the line. So the thus the you have a, you will come across a drop in the voltage, but it will not be exactly much larger drop here. All right, so you get a drop in the voltage, but when the fault is cleared, then again the voltage will rise. But it is possible that you come across some oscillation in the voltage curve, yeah, voltage profile. So thus for few seconds following the disturbance, though it was a temporary disturbance, you come across a voltage oscillation. And what you get actually, it is basically a drop in the voltage. And let's say the voltage oscillation magnitude, it is something up to 20%. So that means you get a dip up to 20% here, something. So this is the one. So from 1 per unit up to 20%, or maybe 10 by 10% even. So you get a voltage dip here. Then you have something we can analyze. What is the because if I define 20% voltage dip here, then this is the more serious case situation. Then we say that it is the maximum transient voltage dip. And then we say what is the duration for which you come across a transient voltage dip here. So they measure it actually. And then it will be important that how you can compensate or how you can improve the voltage uh, during the transient period here. So it is this duration where you get a voltage dip exceeding 20% here, right? And thereafter, again, if you are able to provide some way of compensation, then you can improve your voltage profile here. So you can improve, then let's say it may not be exactly in few seconds, but it will take some time to uh, improve the voltage profile. So you can say the voltage improvement takes place after the disturbance in few minutes. So that means at the later stage, you are able to compensate and thereby improve the voltage here. So, but again, depending upon what situation you have, you may have some deviation from the nominal value, or you may not have some deviation. That is possible. So that's there are some of the terms which we call it as performance parameter here. So we say what is the maximum transient voltage dip, which you get it here. So what is the this value, and then what was the initial value? This one. Do you remember similar term we have defined it for frequency? Do you remember?
Like the maximum frequency dip.
Yeah, maximum frequency dip. What was that known as?
I don't remember now.
Nadir. Do you remember this nadir? We call it as nadir. This quantity. So that is this one, right? So the maximum frequency dip there we say at nadir here. The same thing over here also we have said it. But here we have defined in terms of some percentage here. So what is the dip? So same way you can also define it for frequency, no problem. You can define it. So thus we have some councils. In fact, I was looking at StartNet, but I could not get enough information. Otherwise, I could have provided you here in discussion. But there are some councils here, and so they have some standardization uh, about the voltage requirement whenever you have some contingency. So either the load generator outage, line trip, or the load trip, and so on. So whatever the contingency that takes place, so they have some standardization towards the requirement of the voltage of the buses. So they say that the voltage should dip should not be more than this one at the load buses, or then for non-load buses, it should not be this much. And again, they say that the voltage should not exceed 20% for these many cycles. So that means here they have defined 20 cycles. Yeah. So that means what is the time frame? So that for this much 20 cycles, the voltage should not be more than 20% here dip. I mean the voltage dip should not exceed 20% here for these many cycles at the load buses.
20 cycles means like less than half a second, right?
20 cycles, yeah, 50 hertz, 20 millisecond.
Yeah.
Yeah, 50 hertz, 20 millisecond. So one cycle, 20 millisecond. So here they say 20 cycles. So 20 cycles into 20 milliseconds. Am I right?
So 400 milliseconds. Yeah, less than half a second. Yeah, as I said.
Yeah. And then the post transient voltage deviation that should not exceed 5%. That means here. That means towards the steady state. Towards the steady state, the voltage dip should not be more than 5% at any of the buses. At any other, that means we have to apply some way of control action whenever you have a contingency, right? The voltages that should not go down, that should not go beyond 25% of the load buses or 30% at the non-load buses, and again for this much time duration. And then following the event is the voltage dip should not be more than 5% here. So that means at steady state, because when you said the post transient situation, so this is something like in some minutes or after that, the voltage should not be the voltage deviation, because this quantity is voltage deviation. So the voltage deviation should not be beyond this value here at any of the buses here. right? Yeah, next one. Yeah, as I said in the when we on the first slide, that it is very tricky to uh, to have the compensation or the balance, or to achieve a balance of reactive power, because in case of active power balance, it is source is your generation and the turbine, and your consumption sink is your load, right? Consumption load, but nothing in between the source and your load for active power balance. But when you talk about reactive power balance, then you have generation and the sink, absorption of reactive power at several stages, right? And you can see that all these components are involved in generation and absorption of reactive power. So because, but for active power, it was only the generator and your load, nothing line. Line was not involved in the balancing the active power, cable, transformer, or in some devices. For active power balance, it is your generator turbine against the load. But for reactive power, there are the situation is a little bit different, because for reactive power, these are the components which are involved. And you can see the generator, the first one, if I say the generator. So if I have now again, normally generator, synchronous generator, we have it is with excitation, right? And in normal operation, the synchronous generator is overexcited because we want to get the generator terminal voltage. So that means you have a field current. You have a field current in the field winding of the generator somewhat more than the rated value, higher value. Right. So thus you have the overexcited synchronous generator. And in that situation, the generator will supply a lagging current, and thus you have a inductive reactive power flow from the generator. So, so that means the lagging reactive power flows to the load, and it is from the generator, right? So thus the generator supplies reactive power, inductive generator. When it is overexcited, then the generator supplies inductive reactive power to the load. However, though we will never come across this situation, because in normal operation the generator is overexcited, but still we can say a case that if the generator is underexcited, then again it will supply uh, leading current to the load, and thus the you can say the current flow from the generator will be capacitive reactive power flow. However, the low, if you take about another one, overhead line, uh, line can supply reactive power, or the line can absorb reactive power. So this is the sink here now, and this will be the source of reactive power. So if the line, overhead line, supplies reactive power, it is a source of reactive power. But if your line uh, absorbs reactive power, so this will be the sink. Can you tell me the situation when you can come across this?
Does
Yeah.
it depend on the length of the line?
Length of the line and then operating condition.
Mhm.
Yeah. Do you know the Ferranti effect?
The what?
Ferranti effect.
No.
Uh, maybe Ferranti effect. So it is said that mainly for overhead line, and a long transmission line. All right, long transmission line. And if that long overhead transmission line is lightly loaded or no loaded, right? Let's say this is your bus and this is your another bus. So here you have V1 and here you have V2. And this is your load here and here is your source, right? So if this bus is lightly loaded, or let's say you have 5% load connected or 10% load connected here, or it is at no load condition, then we find that V2 is greater than V1. So that means the voltage at this end, all right, the voltage at this end becomes more than sending end. This is the sending end because this is you have the power flow in this direction, right? And this is the receiving end, right? Where because you have the load connected here. So if you have a no load connected, there is no load, or it is there is a light load connected on this bus, then the voltage here can be more than this one. Why?
I think it's because of the capacitance of the
Yeah,
line.
because the capacitance is greater than your inductance. Because you have a high voltage, let's say 400 kV line, something, and for a longer duration, longer length, I mean, let's say 200, 300 kilometer, 500 kilometer. Then we find that because capacitance of the line becomes more than inductance of the line. And with this situation of operating condition, light load condition or no load condition, then we find the voltage is greater. This sending end, the receiving end voltage is more than sending end voltage. So it means it is because of C. Capacitance is more than inductance. So if you have capacitance more, so you will have it in fact, the overhead line, so, right? The overhead line will uh, act as a source for reactive power. So if you have higher capacitance, more dominant capacitance, then the line will generate reactive power. But if the inductance is more, if the inductance is more, then the line can absorb reactive power here, right? That is the situation we come across for overhead line. So the overhead line, depending upon the length of the line and the operating condition. But if the line is heavily loaded, all right, if the line is heavily loaded, let's say here you have a large amount of load connected, and load will be mainly inductive load, right? Load will be mainly inductive load. And then if it is a heavily loaded, then you have a inductive current flow. You will have an inductive current flow. And then in that case, the overhead line itself can absorb reactive power. And thus the overhead line can be a source for reactive power, or it can be a sink for reactive power here. Similarly, when you look at cable, in case of cable, it is something little bit different because in case of cable, capacitance will be always more than inductance, because in case of cable, the conductors are placed closer together and you have a dielectric medium between these phase conductors, I mean, right? And thus the capacitance is much higher. So for a cable will be always a source for reactive power here, and thus the cable will always supply reactive power. So we don't have this situation, absorption of reactive power in the cable. We don't have it. Similarly, if you look at transformer will be always inductive. So it will always absorb reactive power. So transformer cannot generate reactive power. Then again, the load, yes. Load cannot be a source for reactive power. It is always absorb, sink. It will be always a sink. Then, So here we have the generator, we have components. So it could be line, overhead line, it could be underground cable, it could be transformer, it could be the load. So these are the components in your power network, which can be a source, which can be a sink for reactive power, right? So does the situation is little bit tricky when you have to maintain a balance between the reactive power generation and absorption of reactive power, because you have the generator, you have the line, you have the cable, you have the transformer, and the load as well, which is uh, always time varying. So it is very tricky to maintain a balance of reactive power in your complete network. So it will be important to maintain a balance of reactive power, and that will be through your compensating devices. Because reactive power sometimes could be more, sometimes it could be less, right? Sometimes you may have reactive power generation, sometimes you may have reactive power absorption, but we want the voltage, right? Because if you have more reactive power than the required, right, then what will be the voltage? Voltage will be more. But if you have more reactive power absorbed with respect to reactive power generation from the overall system, then the voltage will drop. So we have to get a voltage to the rated value, and thus we need to have some way of compensation through compensating devices here. And these compensating devices can generate reactive power, and also it can absorb reactive power. So the compensating devices can absorb or it can generate reactive power, both. It will have the capability, it will be able to generate reactive power or it can absorb reactive power. Yeah, so that we are able to maintain a reactive power balance and thereby the voltage of the buses to the nominal value here. So do we have a break here for some time?
Okay.
Okay. So so next we move here. So this is here we have the what are the methods for the voltage control, and we start with the generators. So even the generator uh, can be one way to maintain the voltage, but this will be only on the generator buses, right? Not on the load buses or some other buses. It will be only on the generator buses. So the voltage at the generator terminal, we are able to regulate or control through AVR, and that is on the excitation system of the synchronous generator. Then apart from the generators, uh, which will be uh, which will be regulating the voltage only at the generator buses. For other remaining buses, we can have the voltage control through some other devices, and those are basically the compensating devices. And this includes, it could be, as I said, you may have the requirement of reactive power from the compensating devices, either as a source to generate reactive power or as a sink to absorb reactive power. So thus these compensating devices, uh, they should be either as a source or sink of reactive power, volt ampere reactive. So if you only include shunt capacitors, then they will be as a source for reactive power. If you use shunt reactors only, then they will be a sink for reactive power. Similarly, we have the use of synchronous condenser, and these are also as a source for reactive power. Uh, have you heard of synchronous condenser? What is this one? Because condenser
Yeah,
means like
I've heard
capacitor,
about that.
but
It's
here they have the term synchronous. What is this?
I think it's a generator that is operated to only supply and receive reactive power, right?
But it's not a generator, but it's a synchronous motor.
Mm-hmm.
So when you have a synchronous motor, so in fact, it will be not the traditional conventional synchronous motor, but it has to be specifically designed for compensation purpose. Because synchronous motor, when they are overexcited, they can supply leading power factor current to the system. So we want overexcited synchronous motor. And to have overexcited means you need to have more field current. And to have more field current means the field windings, the field turns, the field winding, the copper winding has to be more as compared to conventional synchronous motor. And thus the size of the synchronous motor which is to be used as synchronous condenser will be more than the conventional synchronous motor. Right, so it is overexcited synchronous motor which can supply leading current to the system and thereby improve the voltage profile. Then we have static var compensators, because here we said only the capacitors or only the reactors, but we want compensating devices which can supply or which can absorb. So these compensators, so these are static var compensators which can have both capacitor bank as well as inductor bank. So these static var compensator, they will have both capacitor bank and reactor bank towards the compensation here. So these are the sources or the sinks. And then we also have in some cases the use of series capacitors, and which can compensate the line inductance here. So it means that because these devices, so what you talked about, these are placed in the shunt, because that means they will be across the line. That means what I mean to say, between the line and the ground here, right? It will be between for each phase. But series capacitors, they are in series with the line. So it means that let's say you have, this is the line, this is the bus here, and then you have one capacitor here, series capacitor plays with the bus. So this is the bus 1 and this is the bus 2, and here you have series capacitor placed, right? So it is in series with the line. So this could have some, let's say, capacitive reactance of the series capacitor. Yeah. And let's say the line inductance is XL, total line inductance is XL. So what is the net inductance of the line? Net. It will be something like XL
Minus XC.
minus XA. Yeah. So it is this way. So thus the net reactance of the line can be effectively reduce here. I mean, so we can have the use of series capacitor, but normally we don't use it. But in some situations we have it in application. Then these are the devices which we use for, although synchronous condenser we don't use on transmission network. Mainly we have them in a larger industrial unit or at a distribution network. Yeah, mainly. They cannot be for, let's say, supplying reactive power in the range of 100 MVA, 200 MVA, and so on. But for few MVA, let's say 10 MVA, 25 MVA, something, so they can be used. And thus they are connected at a lower network. So it could be like a distribution network. Yeah. Then for the distribution network, we also have the use of regulating transformers. So they are nothing but the tap changing transformers or the boosters. So, but they have it, they are connected at distribution network. So regulating transformer and the synchronous condenser, we have them at distribution network. But for transmission network, you can have shunt capacitor, reactors, or static wire compensators, including series capacitor here. Right. So here, this one, just wait. Mm, okay. So here, just wanted to give you illustration about what are the control, and but we have already discussed earlier uh, what are the elements on the control for generator side. So because you refer to the generator, then coupled to the turbine, and then you have a steam inlet. So the governor part here, and we have the active power control or the load frequency control here. But if you refer from the generator terminal, we have the measurement of voltage signal, AVR, excitation system, and then the generator field winding. So that is this is the loop, you can say, which is involved in controlling the voltage on the generator side. And here, this is the generator capability curve. And as I said earlier, that it shows this is on this axis, it is the Q, volt ampere reactive Q, and on this axis, it is the power, megawatt here, active power. Now, we define a boundary for the operating region of the synchronous generator. And where what you can see that when the generator is overexcited, when you have a higher field current than the rated value, uh, it is lagging reactive power. So the generator will supply lagging reactive power to the load here when it is overexcited. So you can see that as you have the increase in the loading, that is the active power. So in fact, uh, the loading on the generator, right? The loading on the generator, the active power, right, on the generator loading is limited by the maximum power rating of the turbine coupled to the generator. So that means up to what capacity of turbine is coupled to the generator. So this is the amount of power which is limited from the generator here. Right. So you cannot have more power as an output from the generator that is more than the turbine rating, right? So that's the limit. It is up to this much. Yeah. Then again, there is a limit on the stator current flow in the generator, and that because when the generator is loaded, then the current flow in the stator winding is it includes active component of current flow and uh, reactive component for the component of the current flow, because generator is connected to the load, and the load is inductive in nature. So the maximum current flow in the stator winding of the generator, it is limited, and it is limited due to the heat loss, heat generation in the stator winding. That is the maximum current flow. Then again, the maximum value of excitation, that means the maximum value of field current flow in the field winding, that is also limited, because again because the field current flow in the field winding will generate heat in the excitation in the field circuit here. So again it is limited. So that means we have a limit on the maximum value of field current here. We have a limit on the maximum value of stator current here. So, and thus we have a complete boundary defined and for the operation of the generator. And this refers to the capability curve for the generator here. Now, as shown on this curve, to illustrate you here, this one. If I say the generator power factor is 0.8 lagging, so it will be this much amount of active power and this much amount of reactive power. So with the 0.8 power factor lagging, this is the active power, and this is the lagging reactive power supplied by your generator here. So this one. Then here on the capability curve, they define that this one, in fact, because at this point, reactive power is zero, Q is zero, and this will be achievable. This will be achievable when you have power factor unity, and that refers to normal excitation for the synchronous generator. So with the unity power factor, this will be the maximum active power flow from the generator, but in that situation, no reactive power flow from the generator. So again, it is also important that uh, since I said that the generator is overexcited. So if you have the generator overexcited, there will be some amount of active power and there will be some amount of reactive power flow from the generator here, right? Anything on this one? So that is the operating region. So you may have your generator operated somewhere here, you may have it over here, or but let's say you operate your generator here. What does this mean? Can you say?
That means you're supplying reactive power lagging, or?
You have less active power supply, but
Yeah.
you have more reactive power supply. But generator has to supply active power, but although
Yeah.
some amount of reactive power is required. But again, if you have this operating point, what will be the power factor? Power factor
It
will be
will be less,
poor,
maybe 0.7.
poorer. It will be
Yeah.
poorer, right? So, but because generator is meant to supply active power basically. but again with some proportion of reactive power as well, with some proportion of reactive power. So thus it is preferred that generators should be operating in the range of zero point 0.9 or 0.95 lagging power factor, right? So if you have zero point 0.9 or 0.95 power factor, then you will have this much amount of active power flow, and then you may have something reactive power flow here. So with zero point 0.9 or 0.95 lagging power factor, something, right? Right. So next one. So here the it says that what should be the, why I'm not able to have this remove? Is it some way can do it? This line. Oh, okay, but I have to keep it here. How can I remove this? Anyway, so here we have the requirement for the reactive power on the generator, and it says that it should generator should be capable to generate reactive power so as to have the voltage as per the schedule value. So it says that if you have 230 kV system, I mean the bus voltage, then to where you have the generator connected, so the voltage uh, 1.02 per unit something, you should have the control of reactive power on the generator connecting to the bus above this value. So it is 1.02 per unit. And then if you have a bus up to 230 kV to where you have the generator connected, then you should control your reactive power so as to get 1.01 per unit. And if in case you have your generator connected to this range of the bus voltage, then you control your reactive power on the generator to maintain the voltage something 1 per unit. So what does this mean? Yeah. So that means here you have higher voltage. So that means little bit of more excitation. Am I right? As compared to, because if I say if you go back to the capability curve here, so because you have more reactive power, if you have more in fact reactive power, and thereby that means we have to control the reactive power of your generator and thereby maintain the voltage either 1.01 per unit or maintain it 1.02 per unit here, right? And next one, as I said, yeah, generator should have the reactive power capability to maintain the power factor in this range. So it is 0.95 lagging to 0.97 leading. So that means both it is considered here. And yes, it has to be automatically performed through the voltage regulator. And they should also be required to operate to the maximum reactive power capability so that the desired voltage can be can be met, right? And also it is said that we may have some reactive resource to be ensured. That is another part here. I have to okay, what are the other voltage control equipment, and they are listed here, but all those are passive equipments. which are, that means they are designed to permanently supply reactive power, right? So, but they can be either fixed or they can be switchable, and it could be through circuit breaker or switches here. So you may have these passive devices, compensated devices, either permanently connected to the line, I mean the bus, or it can be switchable depending upon. So you have the shunt capacitors, which will supply reactive power, and the amount of reactive power supply will depend upon, sorry, this is voltage square here, to the system where it is connected. And with shunt compensator, you experience a voltage increase to the location where it is connected, I mean. Next one is the reactor, shunt reactor. They absorb reactive power, but again, it will be locally, right? And then they can result to reduce the voltage locally. So you can see that these devices, they are effective. They are effective uh, in achieving the power balance, reactive power balance, and regulating the voltage locally. Next one is the series capacitor. It can reduce the reactance of the line, right? But this is okay. Uh, they can be self-regulating, but disadvantage in some cases we find that they can result into subsynchronous resonance. Yeah, we have not discussed this, but maybe later we can discuss that. That means they can result into excitation of a mode, uh, let's say something in the range of 10 hertz or 15 hertz or 20 hertz, something. So you may have a subsynchronous resonance being observed whenever you have the series capacitor introduced into the circuit. Yeah. Then another one is the series reactor. Again, the same way. Actually, here you can increase the inductive reactance, overall inductive reactance here in the system. But we have the use of series reactor in the system. So this is the slides to show uh, about the shunt compensation, and we have, as you can see, these are the shunt capacitors, the shunt compensators. They will supply reactive power and improve the voltage locally. Right. So do you understand when I say the local voltage improvement?
You mean at the distribution level, like substation?
Uh, what I mean to say that let's say if you have several buses here, right? You have several buses in the system and they are interconnected, right? And but let's say on this bus you have a shunt capacitor connected here, right? Shunt capacitor, you have this one, and let's say you also have shunt capacitor here, right? Now the system is interconnected, but at few buses you have the shunt capacitor here. Now when I say that the voltage improvement is locally, it means that it will improve the voltage at this bus only. It will be difficult to achieve or the improvement in the voltage at this bus. At a remote end, it will be difficult. This is what it refers here. So mainly you connect the shunt capacitors at the load buses because uh, it is the load which is variable. You may have light load condition, you may have heavy load condition, right? So if you have a light load condition, you may have, let's say, the voltage increase. If you have heavy load condition, then you may have voltage decrease, right? Because you have your load which is variable here. So, so thus the voltage deviation from the nominal value you mainly come across at the load buses, not at generator buses, not at some other non-load buses. So thus it is preferred to have the shunt capacitor at the load buses only, right? And thereby improve the voltage profile at the load buses whenever you have a load changes here. So, and thus it is required that the voltage improvement because this can improve the voltage locally. It does not, if I say, for example, you connect your capacitor here, but your load is here. And let's say that you want to improve the voltage at this bus where you have the load connected with a capacitor connected here. So in that case, let's say there is a transmission network connection. Then this capacitor has to compensate this much amount of reactive power also through the line. So this is not a good design, in fact. So it is said that uh, you compensate your reactive power demand from your load locally rather than from a remote end. So that's why we say that the compensation has to be across the load, parallel to the load here, and thus the locally done. Yeah. Right. And then you can have because you can have the use of some capacitor. This can be switched. In fact, it can be switched either to control normal daily fluctuations in the system voltage level. Whenever you have the load changes and thereby resulting into voltage deviation, so this capacitor can be switched in. We have the sub, as we can see, even at the distribution network, we have them, and mainly towards power factor improvement. So as you can see here, this is figure shown for power factor improvement for a industrial unit here. So you have a power supply from the utility grid through the transformer you have, right? And then you step down, this is a common bus, and then you have some large load here. So when you have a large motor load, so thus these large motor load require individual compensation through the capacitor here. So you have a shunt capacitor connected on each motor. So this is the individual compensation. You may also have, let's say, some other small motor load, and let's say you have several motor loads, small size. For them, it is possible to have a group compensation rather than having an individual compensation because these motors, they are of a small size, so you can have them in a group compensation. Then again, you can see that for the overall plant level, we also have compensation at this end or maybe at this common bus bar. So this could be as a plant compensation here, right? And these shunt capacitors, they are also in transmission network where you have bulk amount of power flow to maintain the voltage in the system here. So here it's shown, you can see that we have those buses, and then you may have the shunt compensation, which could be, because this is the capacitor, so it could be a source for reactive power generation here. Right. So maybe we stop here if you have some query.